Hello and welcome to graphing rational functions. We're going to begin by graphing the reciprocal parent function, and that reciprocal parent function is also known as the rational parent function. So if you do see the word reciprocal, just remember that we are dealing with rational when we are dealing with that. All right, the rational parent function is a parent function we studied earlier in the year. We're just going to bring it back to the forefront right now so that you guys can see exactly what it is you're supposed to be transforming and what the parent function looks like from all aspects. So I'm simply going to use the table values above to graph on the parent function on the graph below. All right, there's behavior that the rational parent function has that is unique and only to that function. So we'll talk about that in a little bit in just a moment. That behavior is this bend that you see in the graph here. The bend is the behavior of moving about or around asymptotes. Asymptotes are values or lines that a graph will approach but never touch, and there are some specific rules that govern where those lines are, how they show up, and why the graph behaves the way it does around them. The horizontal asymptote in the rational parent function is y equals 0. The vertical asymptote in the rational parent function is x equals 0. Because these asymptotes fall on both the x and y axis, the y-intercept and the x-intercept do not exist. That's what DNE stands for. You'll see error in your calculator, and another term you'll see is undefined. Rational parent functions have a domain which encompasses all real numbers, but it will never equal whatever the vertical asymptote is. So it'll always be all real numbers with the exception of whatever the vertical asymptote is. In this case, it cannot equal 0. Range, generally speaking, will follow the same rules as the domain. However, because rational parent functions behave badly, there are some exceptions to this which you will encounter in the upcoming days. So in general terms, the range is going to be all real numbers except where the horizontal asymptotes lie. But in some cases, some rare exceptions, it will cross the horizontal asymptote. And we'll talk about that also as we get into it. We're going to talk about transformations of parent functions. The transformations of parent functions are no different from the parent functions that we've seen before. We still have A, B, H, and K. We're not going to focus on B, we're just going to focus on A. So A is going to be your value here, which will represent your vertical stretch or compression. Likewise, if it's negative, you'll have a reflection vertically. H is going to be inside the denominator with the x, which makes it inside the function, and that's going to be your shift right or left, opposite of what you think. K is going to be the value on the outside of the function. That's going to be the same effect as what you think. All right, we're going to use our reciprocal parent function as a guide to help us sketch these graphs in these examples so you guys can get a good idea about how all of this works. So the first thing I'm going to do is I'm going to list my transformations. Since this value is 1, that means A is 1. There will be no vertical stretch or compression. It's because it's a positive number, there will be no reflection either, but the 3 and the 5 represent a move to the left and a move down. We're going to use those to help us out. Now, the way that I like to draw the rational parent function is by starting with its asymptotes. So if the parent function has asymptotes at 0 and 0, that's y equals 0 and x equals 0, that means this transformed rational function is going to have a vertical asymptote at -3 and a horizontal asymptote at -5. So I'll begin by drawing those now. Now that the graph has been, the asymptotes have been drawn, now I can sketch what happens by using the parent function as my guide. And then this one belongs down here in this area. Now that we have that, now we're able to figure out the rest of the behavior. So horizontal asymptote is going to be y equals -5. The vertical asymptote is x equals -3. Remember, asymptotes are lines, so that's why we always start with y equals and x equals. The x-intercept and the y-intercept are going to be found by calculating when the x values and the y values are 0 respectively. Okay? So we'll start with the y-intercept. The y-intercept is found when x equals 0. So we do y equals -0 plus 3 minus 5. That's going to give me a value of y equals 1/3 minus, we're going to go ahead and make that 15/3. So that means that y equals -14/3 will be the y value of the y value of the y-intercept. So it's going to be 0, -14/3. Based on our drawing, 14/3, that's going to be a little bit less than 3. Looks like I was a little bit off on my drawing, but that's okay. It's pretty close. All right, the x-intercept is found in the same way. I'll go ahead and make myself a little space here, except now it's going to be y equals 0. So it's going to be 1x plus 3 minus 5. So we'll add 5 to both sides, and we get 5 equals 1/x plus 3. I'm going to multiply both sides by x plus 3. And that's going to give me 5x plus 15 equals 1. I'm going to subtract my 15 to the other side, and I get 5x equals -15, which means x equals, Mr. Hunter's causing problems for myself. Sorry about that. Let's try again. Forgot about the 1 there. So that means that 5x equals 1 minus 15, which is 14. So we get x equals -14/5. And that's going to give us that value right there. And we will go ahead and put that in as an ordered pair. -14/5 and 0. Okay? The domain is going to be all real numbers, so I'll go ahead and use that, all real numbers. But I'm going to use the exception of x cannot equal -3. Put brackets around that. I'll do interval notation for this one so you can see the difference. -infinity to -5. And then we'll use the union symbol here, -5 to infinity. And that's how we would use it for set notation and interval notation, respectively. All right, let's try another example. In this particular case, we've got two transformations once again. We've got a vertical reflection and we moved up 2. All right, the horizontal asymptote is going to be y equals 2 because of the movement. The vertical asymptote is x equals 0 because there is no movement. I'll go ahead and start there. Vertical line at 0 and horizontal line at 2. Now, what was in the positive portion of the graph now reflects vertically downward. So that means this one will change to here. What was negative down here in this part of the graph, or this quadrant, is now going to be reflected to the positive side. So this one is going to be here. All right? Now what we're going to do is we're going to fill out the rest of the information. The y-intercept is the place where the graph equals when x equals 0. So let's plug that in real fast so that we can see logically that we have an issue here. Can we have 0 in the denominator? The answer is no. We confirm that by the placement of the vertical asymptote. The graph will never cross the x-axis, or the y-axis, which means there is no y-intercept. So we'll go ahead and use the term does not exist. The x-intercept is going to be found in the same way, but 0 equals -1 divided by x plus 2. Subtract 2 to both sides, and that's -2 equals -1 over x. Multiply both sides by x, and then we get -2x equals -1. Divide both sides by -2, and we get x equals 1/2. And our x-intercept is going to be 1/2 and 0, written as an ordered pair. The domain in set notation is going to be all real numbers. X cannot equal 0. Range in interval notation is -∞ to 2 and 2 to infinity. All right? It doesn't matter which way you write your notation unless it specifically states which way you're supposed to do that. Okay? What I'd like you to do next is I'd like you to practice the remaining 2 graphs on your own, please. They are both the same graph, but one undergoes more transformations than the other. So you're going to be building from question 4 on to question number 5, okay? I'll be checking this at the beginning of class tomorrow, so be prepared to demonstrate what you know and how well you can transform the reciprocal or the rational parent function.